So I'll talk about energy efficient communication and computing, really just about how communication can affect computing. I won't really talk about computing itself, but data centers and high performance computing in particular. And there's a group of us at UCSB are working in this general area. In particular, Rod's been doing this his entire career, and Dan Blumenthal, Larry Calder, Nader Daghli, Adil Saleh, and Luke Thigaraj, and myself. So get into that. So the problem that we have that we're all facing, the topic of the seminar today, is the increasing energy consumption. And in fact, it's having on our limited oil supply and causing financial strain, sending $1 billion a day to the Mideast, and political upheaval when these sources are not available. But the point is that we waste more energy than we use, so there's plenty of room for improved efficiency. And this is a plot of energy usage per person or per capita. It's a function of GDP. And indeed, the US is up here leading in terms of energy consumption. So the point being that we need to develop new technologies to improve energy efficiency. And that's what the focus of the Institute for Energy Efficiency is about. And it encompasses a lot of centers and a lot of faculty across campus, from Bren through sciences to College of Engineering. You've heard from Steve in the lighting area, and Umesh will talk next in the electronics area. And I'll talk about sort of photonics and computing. And there's other good areas. Igor Mezik runs a building effort, and Alan Heeger and others working in production and photovoltaics. And then a number of people at Bren and elsewhere working on economics and policy. So that's the scope of what the Institute is about. I'll focus now on just photonics end of it. In terms of the internet, I think, as you're aware, there are now over 2 billion people using the internet and doing more than 1 billion searches a day. That's an amazing amount. And the data growth that we're seeing as a result of this is relatively unbelievable. Literally something like 1 billion views per day on YouTube and gaining 24 hours of video every minute. That's a staggering amount of data to be stored. This data that we're storing is plotted here. And if you look, in fact, I added a guide here at the bottom. For those who are not up in zettabytes, 10 to the 21. We're now at something like 2 zettabytes per year today. And that's a phenomenal amount of data to store, to transmit, to search. And that's sort of what photonics is all about now, is how do you transmit that data around. So this is the plot of all of the submarine cables that have been built now around the world. And Jim, you may have a problem with yours, but there was also a problem actually in the earthquake. In Japan, 3 of the cables were knocked out by the earthquake. And so you'd think these things lying down at the bottom of the ocean would really be quite robust, but obviously that was pretty major impact. So each of these has increasing capacity over what happened before. And fortunately, each of those is incredibly more efficient than what happened before. So in terms of capacity, this is sort of what one could put down an optical fiber. Now, this is research results. This is not what production stuff is yet. It's sort of production lags down here by about a factor of 6 or almost order of magnitude. What's kind of exciting, the most recent result is up here. This was presented just a couple of weeks ago at the Optical Fiber Communication Conference. But people are now putting 305 terabits per second on a single fiber. That's an amazing amount of information. And it encompasses all the stuff that's been going on from the beginning. The original system, this is back when Rod Alfred started his career. The first fiber optic system was 50 megabit per second. It's actually down here about the floor, actually, on this scale. And then going up to here is just higher and higher speed, so time division multiplexing. And then something that Rod very much worked on and Adil Saleh throughout their careers is wavelength division multiplexing, and then phase effects and coherent communications. And most recently, the space division multiplexing is what's gotten us up here. And so now this fiber has 19 cores. So it's one fiber, but 19 cores. And we're now able to excite all those cores efficiently and pull the information off efficiently. And I think we all keep thinking this is going to saturate sometime soon, but it doesn't seem to yet. But this is the exciting part from an energy point of view. These are all the transatlantic cables. and looking at how much energy it took to get a bit across the, well, for 1,000 kilometers, but for a transatlantic distance. And what you see here is that from the first transatlantic cables up here down to where we are today, that's 500 million times less energy than it took before. That's an amazing reduction. And if you look just over the fiber optic era, this is from here, TAT8 was the first fiber optic cable, down to here, it's more than a factor of 1,000 reduction in energy per bit. So that's the good news, and that's what's enabled this rapid increase in data transmission. So these are submarine cables. This is the terrestrial average, so for all the cables that go around between buildings and states and on land. This is the traffic that's being transmitted. So this is from relatively recent, from here, say 2010. If you go 1 decade, it's projected to be something like 100 times more data traffic. And that's certainly what has been going on for the last 30 years. But that's what we have to deal with. We don't want to use 100 times as much power in just 8 years from now. So the question is, how do we do this more and more efficiently? How do we continue that down? Some of the good things about fiber optic transmission and teleconferencing is you're all here, fortunately, but probably 1,000 times more people will watch these presentations by downloading them over the web. And indeed, that takes a lot less energy to see it than traveling here to see the talk. So one example is calculated by Rod Tucker was, if you look at how much energy it takes to fly to a conference in Santa Barbara, it's something like 5,000 kilograms of CO2 emission. And if you do this with video conferencing, even very good video conferencing, a gigabit per second, that's at least a factor of 300 times less CO2. And I think we should be able to do with data compression and things much better than that. So that's the good news about this. Now going back to data centers, and data centers today are very efficient, but the amount of energy being used in data centers is growing very rapidly, and that's the issue we need to address. This is a picture of a typical large data center, 50 megawatt sort of data center. And if you look at the amount of cooling power it takes, which is in the yellow, power and cooling, it's rising rapidly, such that, well, this is the cost of it. So the cost of the electronic servers, the computers and things, has been fairly constant, around $60 billion. But the cost of cooling and heating is, providing power to these and cooling for it is rising rapidly to be almost the same sort of number. In terms of CO2 emissions, data centers look to be relatively minor compared to airlines and other sorts of things, or compared to comparable countries in the world. But the problem is, in just 8 years, that number is predicted to be much, much higher, such that this is a problem that we need to deal with. We do need to make much more efficient data centers and much more efficient supercomputers, which we'll get to next. So the good news is Google indeed is doing a great job at organizing all of this data, and this is much more efficient, right? We don't need fast computers at home. We don't need lots of storage. We just need a nice little handheld interface that doesn't take much power, and we don't need to duplicate our data at home and at work and in other places. So that's the good news about it, but the question is, how do we now do this more efficiently? So one of the efforts at UCSB is what Fred Chong leads. He's got a nice Google grant looking at how do you make more efficient data centers? How do you solve this in a software manner? And more recently, how do you solve it in a hardware manner? He's looking at using thermoelectrics to do spot cooling, right? Rather than cool the entire data center, cool just the hottest points of that data center. And that looks to save something like 25% over where we are today. So that's kind of the research he's working on. In fact, there's a workshop that he led whose report is outside, if anyone's interested in reading that. Within the data center, this is a poorly planned data center, admittedly. There's a lot of optical fiber and connecting all these servers together. If it's done in a more upfront manner, then it's a lot more organized. These optical fibers coming off are all bundled together. But modern data centers have millions of optical fibers in them. And so we need to look at how do you make each of those more efficient. A similar problem exists in supercomputing. So this is all the different supercomputers. It's a little out of date, so we're missing the most recent couple up here. And this plot is a little funny. So this is, petaflops going higher, so up is good. And what's plotted this way is sort of inverse power. So what we'd like to be is, this corner is ideal, but this is sort of where it is now. So as you get faster and faster supercomputers, it takes more and more power, upwards of 10 megawatts. But this is just a petaflop, and people are now talking about exascale computers. So 1,000 times that. We don't really want to be running 10 gigawatts into an exascale computer. And so the question is, how do we do better than this? And part of the answer is providing more interconnects that are more efficient. And this red line is if we went to 4 petajoule per bit, and I'll talk a lot about petajoules, so keep that as a metric in mind. And if we can do better than that, which is up here, this is if we can do 0.4 petajoules per bit. So when I talk about putting photonics on silicon, we believe we can hit this level below, picojoule per bit. And what that gives us is a factor of 100 improvement in performance. And this calculation here, this green curve, does assume that basically we can get our interconnects onto this chip. So we need to get the photonics all the way down to the chip to see this. So these two cases are very similar. Data centers and exascale computing have a very similar set of needs. So Adel Saleh here has been working on how do we solve these problems, how do we make data centers more efficient from an architectural point of view. And the point being that you have lots and lots of servers, literally millions and soon hundreds of millions of servers in here. And they need to be interconnected. They need to talk to each other. So as you're aware, when you do a search, it may take 5,000 servers to come back with the answer for your search. Those 5,000 servers need to talk to each other and coordinate it. And today that's mostly done electrically, and our goal is basically interconnecting a lot of them optically. So this green area here is what we use in long-distance communication. It doesn't exist in data centers today. But today everything is switched electronically. And every time you electronically switch, it's about a nanojoule per bit, which is a lot of energy. Optically, we can do it more like a picojoule per bit. So that's the goal. And he's been looking very much at architecturally, how do you organize data centers to do this? One of the other points that he's come up with is that basically we need to get the photonics down onto the server itself. And that's not what's the case today. And so that's our goal. That's all the setup for this is we need to get photonics onto the processors so as to get very efficient communication for supercomputers or data centers or long-distance transmission. So these 6 are sort of the 6 things of photonics today. And these are all typically done in different foundries. So this up here, these are gallium arsenide VCSELs. That's a standard in data centers today. These are indium phosphide chips. This is an example of something made here in Larry Calder and Dan Blumenthal's group, but it's another set of foundries today. More used for telecommunications. This is more for data centers, short distance. And then there's a whole silicon photonics industry going on today and making lots of these different devices as shown here. And then there's lithium niobate technologies and isolator technologies and then passives, silicon nitride waveguide technologies. But the problem is that these are the only 2 that emit light. And everything else over here doesn't emit light. They're very inefficient emitters, and that's inherent because silicon has an indirect band gap, and lithium niobate's an isolator, and YIG's an isolator. And so our goal has been, how do we get these technologies integrated together onto silicon? So if you look at what you can do with each of these technologies, and so again, there's whole foundries, many ones around the country and around the world, in gallium arsenide. Great laser emitter, great detector, great modulator, okay for passives, but you can't integrate electronics, and it's not really on a wafer scale. Same thing with indium phosphide. Lithium niobate doesn't have emitters on it. Silicon doesn't have emitters on it. So our goal here is to do heterogeneous indium phosphide on silicon and try and get the whole gambit of what one needs for a photonic integrated circuit. In some recent exciting work, Art Gossard's group is looking at adding gallium arsenide to this mix, in particular gallium arsenide quantum dots on silicon. And is getting some very nice growth of gallium arsenide quantum dots on the silicon wafers. And we're very hopeful that will be a very efficient emitter for a bunch of reasons. So most of our research is taking silicon technology. It's well established. It's obviously on 12-inch. We're working on 8-inch wafers today. And then combining it with indium phosphide, a very efficient emitter, and making complex integrated circuits. The general way we're doing this is taking wafers of silicon, we pattern it, we put waveguides in here so the light is emitted through here, and then we bond material or grow material in Art Gossard's case on top of here. That maybe it's 3,5 indium phosphide or gallium arsenide. And we pattern it and make normal sorts of devices. And we call it hybrid silicon or heterogeneous integration sort of device to combine the best of the indium phosphide materials with the best of the silicon materials. This is the laser structure as one example. This is the waveguide that carries the light. And so this, when it's a laser, it lasers along that axis. We put mirrors in the end or put a gradient in the middle. And then this layer is where all the gain comes from that makes what we need to make the laser out of it. And so that's the basic device. And we can make amplifiers that look about the same, modulators look about the same, but those are the sorts of devices. This is an example of some of the wafers that are being made. And these different plots on here are different regions where we bonded 3,5 material to this wafer. And then we can make arrays of devices in this region. And if you zoom in, then you see lots more structure. And there's lots of details about how you go from silicon regions to indium phosphide regions. But you can make a very good laser out of it. This is some work we do in collaboration with Hewlett-Packard. And the goal here is to make, their focus is supercomputers again. And their focus is putting small, low-power lasers on processor wafers. And we started originally up here at levels of about 50 milliamps. And the most recent results are down here around just a few milliamps, which ends up being less than a picojoule per bit. So that's where we want to get to. We also make structures called DFB structures, distributed feedback. These have a grating along the length, and that causes the reflection that causes the device to laze. And the advantage of CMOS is every grating can be different in different regions, so you can make lasing at different wavelengths. And this is the basis of wavelength division multiplexing, combining different colors of light together. Each one of these might carry 100 gigabit of data in particular. And so you put this all together and you'd have a terabit of data out of one waveguide, out of one fiber eventually. We can skip this. We also work a lot of modulators. If you want to go to terabit sorts of speeds, you typically want to modulate the light. That's the basis of the industry today. And there's a lot of work, a lot of research these days on making silicon modulators. And probably the predominant way on silicon is using index variations. The problem is that silicon is centrosymmetric, and it's not electro-optic, and it doesn't have a Kerr effect, doesn't have a Pockels effect. Whereas 3,5 materials have all of those effects, and if you add all of those together, you get all these other little dashed lines, and they add up to something like this, which is something like 10 times the size of what silicon is. And if you get a 10 times larger index shift, that means you need 10 times less power to drive this. And so that's been our focus. And the most recent results are here. This is what's called an electroabsorption modulator. But the point being that we can make modulators on silicon now that are about 74 gigahertz in bandwidth. So we can go upwards of 50 gigabit or even higher. If we had the test equipment, we'd go to 100 gigabit per second, is what we think is possible. The problem is that this takes a fair amount of our power energy budget, 330 femtojoules per bit. And so what we really need to do now is not operate with 50 ohm lines, but rather integrate it with high impedance modulators and amplifiers right up against it. And so that's work we're doing in collaboration with Luc Thiegerajan. And so we're not making modulators that look like this. And they're not quite as fast. They're only 40 gigabit per second. And the bandwidth is a little smaller, 32 gigabit. But the advantage now is that they only take 51 femtojoules per bit, so a sixth of what that other one did. So now if you put the laser and modulator together, we can do something well below a picojoule per bit. So that's what, remember back to that supercomputer calculation, if we get down below a few picojoules per bit, we can now enable a factor of 100 advance in capacity. Because the more these servers talk to each other, the more efficient they are. You don't have to just have more servers. They need to be able to talk to each other. This is a summary of all the modulator work out there. And so going this way is good. Larger bandwidth is good. Higher speed. Going up is good here. This is extinction ratio divided by the voltage. So basically, small voltage takes you further up this curve. And all these blue dots are what everybody has done for world record results for indium phosphide-based modulators, primarily done in Japan. It sort of has all the best results. And all the red ones here are all the silicon modulator work. So this is what everybody's been trying to do to integrate it onto silicon. And they're paying a big price, right? And going from here down to here means you need 5 times more power. That's been the problem. And so we've been pushing this hybrid silicon technology, moving up here. And the latest results look pretty good. They're as good as the very best indium phosphide results. And so that's what's exciting. How do you combine this with electronics? If you're making these in a CMOS fab, you can make it all in the same fab. But that isn't really what we've been doing, because photonic devices are fairly big. They don't need the latest 22 nanometer silicon process. They like something that's a lot cheaper than that. So we typically use processes that are more like a 90 nanometer fab, and then we combine them in parallel with the most advanced CMOS fab. So again, this is very much in collaboration with Luke's work. He's sending out designs in CMOS, and then we're combining them with our photonic devices. And this is one of the projects we have. This is one of our optical chips. So this is an 8x8 switch put together. So any of the 8 ports go to any of the other 8 ports. Remember back to Otto's plot? What he wants to do is have optical switching within this data center. And this is a chip that would let us do it. It would save you literally a factor of 1,000 power in switching that across there. And that's our goal. So what's shown here is this big CMOS chip here next to this. And that was sort of our vision, actually. We drew that up. Luke had nothing to do with that. And then he did the CMOS layout. And it turns out that you can put the driver for this in there. And it fits very nicely right in the center of that. It's only a millimeter at a side is enough to drive that entire chip. And that's the advantage of advanced CMOS. They're very small. So this is kind of what we have in mind, is taking our hybrid silicon wafer, which has lots of other things on it interspersed in here, lasers and modulators and things like this, and dropping CMOS chips into it. And then this is Luke's process now, spinning a polymer over the top and then polishing that down and then interconnecting all those electrically. So this is a wafer out here on the outside, and this is one of his CMOS wafers on the inside. There's a little gap here. We fill that with this polymer, and then we can connect wires across there. So it all looks like one chip when you're done. And this is sort of an example of that. You can see here, or maybe you can see here, but the CMOS chip would fit in the center, and then the other chip is around the outside. And that's what we're doing. So for one last topic, some research that's going on here with Dan Blumenthal is optical interconnects. And now, how do you connect these lasers and detectors and things together? And today, that's primarily done over any distance in interconnects or supercomputers with polymer waveguides, whose losses are up around a dB per centimeter. So up to about 100 dB per meter. And recently, we've been working on silicon nitride waveguides. And they're down here. They started better. This is about 2 years ago. And most recent results are down here. So these are all the ways we've been changing things to get down here. But we've lost about a factor of 100, and we've improved it by a factor of 100 in power. And so we can now make long delay lines. Literally, at this point, a meter-long delay line has only 0.04 dB. That's like 1% of loss. And so you can now think about going 100 meters with this technology, which fits back with what Mark Pinto was talking about. If we could do this on glass in some size, you can now integrate literally arrays of these things together. So going back to what I started with, this is history, past tense. We're on this push of getting less and less energy per bit to send data around. And where that combines is everything long distance today is handled with optics, right? Anything long distance is handled photonically. And everything short distance today is electronic. Chips are connected on, processor to memory electronically. But if we can succeed at putting photonics onto the chip, then we can get to this, basically every electronic chip is talking to every other electronic chip optically. And then that's what we're trying to get to. And obviously the volumes involved in this are not now thousands or tens of thousands, which they're only 1,000 fiber optic cables, and there's only, it's much fewer numbers. You're not talking about billions of connections between processor chips. So, better efficiency is important for data centers. It's better for supercomputers. Photonics today works from a meter to infinity. It's the best, lowest, most efficient way to get there. But what we're focused on now is how do we get this number not to be a meter, but rather to be anything longer than about a centimeter. And so we need lasers on chips, on silicon chips in particular, and we need them to be efficient. They need to be operating below a picojoule per bit, because otherwise it's better just to connect it electrically. So that tells me we need a milliamp threshold, milliamp sorts of powers. We need to get lots of data, not just gigabits of data, but ways to get terabits of data. That's where the high-speed modulators and arrays of modulators come in. And then you need to make it inexpensive. And so our main partners have been Hewlett-Packard and Intel, and this has been their push from the beginning. These chips can't cost more than $1. That's why you need to make them in a CMOS foundry. And ultimately, everything has to just keep getting smaller and smaller. So that's our goal. Thank you.